This is part 2 of the life annuity contract videos. This is the final part of these videos, and the life annuity contracts come from the topic of contingencies in actuarial mathematics. So in this video, I'm going to pick up where I left off and cover guaranteed annuities, so annuities that are guaranteed for a certain time period, and then after that they're contingent on life. And then I'm going to cover continuous annuities, some other annuities and approximations, and then how to deal with select mortality for these life annuity contracts. Okay, so let's start with guaranteed annuities payable annually in advance. So guaranteed annuities in advance. Okay, so the present value random variable for this will be A with these dots on top because it's in advance, max of kx plus 1 and n. Okay, so let's understand this. Why is this the case? Well, if we understand a guaranteed annuity to be an annuity that will pay regardless of whether the life dies or not for a certain number of years, that being n years, and then after that it will continue to pay until this life dies. Now if the life has died within those n years, they'll still receive the payments until the end of the n years, but they won't receive any payments after those n years. Okay, so how does this make sense with this? Well, kx is the quotate future lifetime of a life now aged x. Now, if this person lives for less than n years, in other words, their number of whole years of life that are left is less than n, then that means that I must choose the maximum of kx plus 1 and n, which will be n, because their number of whole years of life that they have left will either be n exactly if they die in that nth year, in which case kx will be n minus 1, and then we have n minus 1 plus 1, which will be n. So then I'm choosing between n, and so the maximum here will be n, or it will be something like where kx is significantly less than the time period specified in, where now I'll be taking something like n minus 6 plus 1, which will just be n minus 5, and then I take the maximum of those two, and it will be n. So the number of payments that will end up occurring will be n number of payments. Now if this person survives for greater than n years, then I will be paying kx plus 1 number of payments. Okay, so that should make sense. So this is the present value random variable. Now if I take the expectation of this, then I get the expected present value for a guaranteed annuity contract payable annually in advance. Now the actuarial notation for this expected present value is this. Okay, so we understand that we have a lowercase a here because it's an annuity contract. We understand that these two dots on top are because it's payable in advance. And then we understand that, so it should be like that. So we understand that this x is here because it's contingent on life. We understand that the term that we're concerned with in this contract is n. So we have two different states for this life. This x for the fact that the payments are contingent on the life of this person, of this policyholder, as well as this n here to state that the payments are contingent on a term as well. Now normally this type of contract would pay up until the life dies, but no longer than for n years. So what we're essentially saying is that it'll stop paying on whichever of these states fail first. So x being the life, So if the life fails first, in other words, if the person dies first, then it stops paying. But if this state fails first, the number of periods, if n periods comes to an end before the person is dead, so if that state fails first, then we will stop paying them at the end of the term. Okay, so that's a temporary annuity. A guaranteed annuity is different in that I have this line on top. So instead of now choosing the state which fails first, I'm choosing the state which fails last. Okay, so now if this person dies within the n years, then that's the first of these states to fail. That means this x here fails. But this is still going. So that means when this eventually runs out and this fails, this n fails, the term runs out of time. Then I stop paying payments. Alternatively, if the term runs out of time first, I don't stop paying payments because that's the first failure of the states. Now I'll only stop paying then when the person dies. Okay, so that's understanding this notation. So what this is just a bar on top of the states x and n. Okay, now this expected present value in terms of annuities that we already know will be equal to this certain annuity for n years payable in advance plus a deferred whole life annuity payable in advance and deferred by n years. Now why does this make sense? Well, if a life is now aged x and here they'll be aged x plus n. Now this represents payments that are certain over here and then contingent on life beyond there. So stop paying when the person dies beyond the age of x plus n. Okay, well, how does that relate to this? Well, an is the certain payments that happen between age x and age x plus n, regardless of whether they die or not. Hence, there's no life status in the statuses for this contract, or the statuses for this contract. Now, this is a deferred whole life annuity for a life aged x, deferred by n years, and that represents these remaining payments beyond age x plus n that are contingent on life. Okay. Now, moving on to the variance of this contract. So that's dealt with the expected present value. Now, or the expectation, now we're dealing with the variance. So the variance of this random variable will be equal to 1 over d squared v to the 2n nqx plus n a x, so double the force of interest here, and minus v to the n nqx plus n ax, and that all squared, and then close my final brackets. Okay, so that's the variance for this. Now, what about guaranteed annuities that are payable annually in advance? So the present value random variable for this type of contract, so let me first write so that we can remember. This is guaranteed annuities in advance. Okay, and the present value random variable will be a max of kx and n, sorry, this should be in arrears. So we've already done in advance. Now I want to do in arrears. And so I won't have those dots. Okay, and that's the present value random variable. Now, if I take the expectation of this random variable, then I get the expected present value, which is in actuarial notation, it's this. Okay, so exactly the same as above, except I've dropped the dots, and I've also dropped this +1 in this term for the annuity, for the present value random variable. So why have I dropped this +1? Well, if it's in arrears, it means I'm foregoing that initial payment that happens at time 0. So I will have one less payment. Okay, so that's why I have kx here, not kx plus 1. Okay, and this equals to an plus a deferred whole life annuity. Okay, now I'm not going to explain this because it's the same reasoning that I used for the guaranteed annuities in advance. Now the variance for this, be careful here, it's not exactly the same. So the variance for A max, kx, and n equals 1 over d squared into v to the 2 into n plus 1 qx plus an whole life assurance deferred by n plus 1 years at double the force of interest minus, in brackets here, v to the n plus 1 qx plus n plus 1 ax, and that bracket squared, and close these bigger brackets. Okay, so that's guaranteed annuities in arrears. Now, it's not enough to just understand what I've said in this video and to know these formulae. It's important that you know how to derive them, and I've stopped deriving all of these formulae because if I were to do it for all of them, it would be tedious and repetitive. But I've already been deriving. I derived some of them earlier in these series of videos, and so if you want to know how to derive these types of things, you should refer to those videos. So yes, you do need to know these formula. You need to know how to derive them. You need to understand them so that you can apply them to any question that has been given. But you also need to know how to use them effectively and quickly and be well practiced with them. So make sure you do a lot of practice where you're actually applying these formulae to different scenarios. Okay, so let's move on to continuous annuities. Okay, so the idea with continuous annuities is that I'm now, instead of paying at the end of each year or at the beginning of each year, contingent on life in some way or another, whether it be a temporary annuity or guaranteed annuity, however it is, or a whole life annuity. Now, continuous annuities, instead of being the payments being at discrete points in time, the payments are going to be at every point in time. So there's a stream of payments, there's a flow of payments. And these payments are also contingent on life or death. Now, this means that payments stop immediately on death, but they could also be guaranteed for a particular term or have a term to it. But the point is that they stop immediately on death, given that the death is outside of some guaranteed term, if we are dealing with a continuous guaranteed annuity. Okay, so these annuities, the difference is that they're paying continuously. Okay, so our present value random variable will be this. So I have Tx here, which is the complete future lifetime of a life-aged X. And this is a random variable in itself, and this is now the present value random variable. Now, I have this bar on top, which you should know from financial maths, representing a continuous annuity. And then the term for this annuity is Tx. So it pays for the complete future lifetime of this life until they die. So this here is a continuous annuity for the whole life of the individual. So this is like a whole life annuity. Okay, and this is the present value random variable. Now if I want the expected present value, then I take the expectation of this present value random variable to get the EPV, the expected present value, and this in actuarial notation equals a bar x, and this equals the integral from 0 to infinity of a t tpx mu x plus t dt. Okay, so I'll explain this in two ways. The first way is you get this by simply using the statistical properties for expectation. When you the formula for expectation of some function of a random variable is that function of the random variable multiplied by the PDF integrated over its entire range for continuous random variables. So now I'm integrating over the range for tx, which is 0 to infinity. This life can theoretically live forever, even though practically they can't. Multiplied, and I'm integrating a bar t, which is this function of the random variable, and this here, tpx mu x plus t, is the PDF of tx. Okay, so that's the first way to understand it. Now let's understand it from a intuitive perspective as opposed to a theoretical derivation. Okay, so intuitively, this annuity is going to pay for a certain number of years t. Okay, and this t must be dependent on the person living up until that time t, and then transitioning out of the state of life to the state of death at age x plus t. Okay, and these possible time points where this can happen, where they must live until time t and then die at that point where payments will stop, and thus the annuity is for t years. All possible points in time where they can die must be slid from 0 to time infinity. So I slide this t from 0 to infinity, and I take into account all possible values for t. So that's intuitive understanding. Now if you then do integration by parts, now I'm not going to derive this in the interest of time, but you should know how to do this. If I do integration by parts, I eventually arrive at 0 to infinity, the integral of 0 to infinity of v to the t tpx dt. Okay, so let's understand this. Well, at any given point in time, if this life is alive, at any point t between 0 and infinity, if this life is alive, I'll be making a payment to them, and that payment should be discounted by t time periods, where v here is the discounting factor, 1 plus I to the negative 1. So vt tpx will discount it in terms of probability and time for any given t. Okay, now the variance for a continuous annuity for this present value random variable, the variance of a bar tx will be equal to 1 over delta squared to a bar x minus a bar x squared, where this a bar x represents a life assurance contract, whole life assurance contract payable immediately on death, and this to double the force of interest. Okay, now moving on, we are going to deal with more special cases of these continuous annuities. So for example, a temporary continuous annuity. This is the expectation of this present value random variable, a bar min of tx and n. Okay, now why the min of tx and n? Because if this person dies within n years, I'll only pay them up until that point that they died. So I'll be choosing tx as opposed to choosing n. But if they survive longer than n years, then I'm only going to pay them up until n years. and I have that bar there because it's continuous. Okay. Now this equals to the integral from 0 to n of v to the t tpx dt. This is exactly the same as above, except for this upper bound, which is n. So I'm taking into account all possible time points that this person could be alive at where I might make a payment to them, but only up until time n. Okay. So they can be a maximum of age x plus n and receive a payment, or still be receiving this continuous flow of payments, but once they're aged x plus n and some, I stop paying them. Okay, so now AX will be equal to AX n plus NAX. I encourage you to think about this, how this makes sense. I've covered it in the previous annuity contracts that I've spoken about, a similar formula, except now I've changed it to be continuous payments. So you should understand how this works. And briefly, a whole life annuity contract will be equal to the temporary annuity, plus the deferred annuity that will start paying after the term. Okay. Then another formula that's important is AXN, the bar there. So this is now a guaranteed annuity contract, which equals AN plus NAX. And I've explained similar formulas to this already, so I'm not going to do that. Okay, then a deferred continuously payable whole life annuity contract will be equal to V to the N NPX A bar X plus N. So it's a whole life annuity from aged X plus N, but now I must also discount it in terms of time and probability 2 times 0 by multiplying by Vn NPX. Okay, now some approximations that are useful. Okay, so we have AX being roughly equal to a dot dot x minus a half. I'm going to explain all of these to you. A bar x being roughly equal to AX plus a half. And then we also have A bar xn being approximately equal to a x n minus a half into 1 minus Vn npx. But this is not as intuitive for me, so I prefer to write this like this, and I'm going to explain all of these in a moment. Okay, so we know previously that AX must be equal to A dot dot X, but one of them has to have a plus 1. So let's figure out which one. So this AX is an annuity contract payable annually in advance. So it has an extra payment to the contract that pays in arrears. So this contract pays in arrears. If I add a 1 to it, then I should get this annuity contract that pays in advance. Okay. Now, a similar concept I'm going to generalize to continuous payments so that I can arrive at these formulae. Okay, and also just a careful note before I do that. In the life assurances contract videos, I wrote some formulae for approximations between a assurance contract that's payable immediately on death and where the death benefits are payable at the end of year of death. There's an approximation that relates those, and I used a claims acceleration approach and a UDD approach. Now those two approximations cannot be used with annuity contracts, and the annuity contract approximations cannot be used with the assurance contracts. Why is this the case? Well, the assurance contracts, so the ones that look like this with the capital A, these assurance contracts typically, or unless it's like a whole life or something, but these have values that exist between, or it's guaranteed for some, so these have values that exist between 0 and 1. Okay, they are relatively small. Why are they relatively small? Because there's only one payment that's occurring. Forget the size of that payment, because the size of that payment we're getting from multiplying this contract by however big the payment is, because we're only dealing with this these contracts for unit payments of 1. Okay, now this, if it only has one payment, the unit of 1 must now be discounted in terms of time and probability, and hence it falls between 0 and 1. Okay, but an annuity contract pays a number of payments until this person dies, or until whatever the stopping condition is. So it'll pay a number of payments, and so these typically have values that are greater than 1, because we're expecting them to receive more than one payment. Okay, so if I use an approximation such as -0.5 on an assurance contract, that means that I'm making a drastic change for a supposedly small change, where I'm just changing how the payment is being made, whether it's paid immediately on death or whether it's paid at the end of year of death. I can't now go and add or subtract a half and completely change the payment of this contract, the present value factor. I can't do that, okay? And likewise, if I just multiply these annuity contracts by 1 plus I to the half, or if I multiply them by I over delta, like I would with assurance contracts, it's not going to make a sufficient change, or the correct, adequate change, in order to have the approximation done effectively, because this is only one payment, but this is dealing with multiple payments. Okay. So back to how we understand this. So let's understand this first formula. I'm going to draw a timeline for you. At age X, this person here will be receiving a payment. At age X plus 1, they'll be receiving a payment. And they'll be receiving payments all the way until they die. Okay. Now, let's say here they die aged X plus N. So between the ages X plus N and X plus N plus 1. So here, they're dying. Okay. That means that payment at age X plus N will be their last payment. But now, if they're dying over here, A bar X would have payments that happen all the way from X continuously up until there, up until the point that they die. Okay, so if I want to approximate these two payment structures to each other, then the only difference is, yes, there's a unit payment that occurs within the first year, and so that accounts for that flat line between age X and X plus 1. There's a unit payment that occurs for the second year, and so there's a flat line that accounts for that between age X plus 1 and X plus 2, and that happens all the way until they die. But now when they're dying in this nth year, or rather in this n plus 1th year, then I will be receiving a payment over here, but I won't be receiving a payment over there. Okay, so the approximation, this A bar, has this extra half. Okay, and so this payment would typically have been for this year from age X plus N to X plus N plus 1. So for this N plus 1th year. So I would have then, to account for that payment, had a flat line between X plus N and X plus N plus 1. But now I don't, because it stops paying immediately on death. And I'm going to assume that the death happened in the middle of the year. So uniform distribution of deaths, or I'm going to assume that deaths on average happen in the middle of the year. I have to make some sort of assumption to make this approximation, and that's one of the assumptions that I'll make. Okay, so once I've made that assumption, then I'm saying that this payment must stop, then roughly it's going to be stopping in the middle of the year. So instead of accounting for this whole time period, I must only account for half of it. So instead then of having this AX where I'm accounting for all n plus 1 years, because I have n plus 1 payments, this is my n plus 1th payment, I must now subtract that half away, that half a payment away. So I subtract half. Okay, that's the understanding of that one. Now, for relating a continuously payable life annuity contract to a life annuity contract that's payable annually in arrears, I must now add the half. Why do I add the half? Well, because in the case where I'm having payments that are in arrears, I don't have that payment over here, and I would otherwise have that payment, but the person died in the year, so I also don't have that payment. Okay, now the difference is that I then, with all of these payments, this payment happens here, and it's accounted for by that flat line. The payment in the next year happens at the end of the year, it's accounted by that flat line. This payment here is accounted by the flat line that precedes it. Now the payment that would happen over here should be accounted by that flat line between age x plus n and x plus n plus 1. But this payment is not occurring. Okay, and I must still account for this amount of time that they must get paid until they die. So from age x plus n to age x plus n plus a half when I'm assuming that they're going to die. So I must then, to this annuity contract that only pays up until age x plus n, this AX, I must also add a half in order to approximate it to this. Now, why do these make sense? Well, on the left-hand side of both of these, I have a bar x. Now, I can then equate those two to each other. So that means that AX dot dot minus a half should be equal to AX plus a half. Now, if I then take that half to the other side, I arrive at this formula. Okay, and that's a sense check to show you that what I've been saying does make sense. Okay, because we fundamentally know this to be true. All right. Now, let's deal with this temporary annuity and why does this make sense? Okay, so this temporary annuity, relating it to the continuous annuity, I subtract this half, as I did in this case, to account for this half that's missing at the start of the year. Okay. But now, at the end of the contract, there is another payment that I must account for. So if I do another drawing, it'll look somewhat similar. Here they're aged X, and here they're aged X plus N, so that's the end of the contract. And here there's all the years that lie between age X and X plus N. Okay, so this pays in advance here, it pays all of these time points until they die. This here will pay continuously until they die over the time period aged X to aged X plus N. Now, it doesn't pay if the life lives beyond that point. So why now do I approximate it with this thing? So this is actually very difficult to understand, and I'm not actually, to be quite honest, completely sure of my understanding of it. There is a proof. You should know that proof. I'm not going to go through it in this video in the interest of time. Again, I'm trying to stay away from proofs because they can only be tested in one way, and I'm trying to do things that can be tested in multiple ways. Okay, so I'll try and explain how I think about it, but I would just recommend that you know this and you memorize it off by heart. And if you do enough practice questions, you'll come across this approximation enough times that you do actually end up memorizing it off by heart. But I'll still try and explain why I roughly think it's minus half and then plus half v to the n npx. So if the person dies within the term, so between ages x and x plus n, we understand why we should subtract this half. We should subtract the half because of the same logic that we subtract the half over here. Okay. So why do we subtract this half v to the n npx? Well, if the person dies outside of the term, so they survive to the end of the term. They survive to some age greater than x plus n. Then, essentially, the payments that were made would have been all of these payments, these discrete payments for this contract, which I'm trying to relate to the continuous payments that happen between age x and all the way up to x plus n. So, as before, if I said this line, this payment is accounted for by that flat line, that payment by that flat line, etc., all the way until that payment by that flat line, then you should notice that these are approximately equal. So if I've subtracted a half, I've subtracted too much. And I've subtracted too much because they're approximately equal. So I must then add something back. And why do I add V and NPX? Well, I add the V and NPX because this half deals with this first payment. But this V and NPX deals with the difference that occurs in this last payment. Okay, so that's pretty much the best understanding I can give you. And to be honest, if I think about it quite deeply, I can find a few flaws with it. For example, why then am I still adding this half if the person dies within the term? But don't think about it too deeply. You're not actually going to be asked to explain the formula, but you do need to know how to use it. So the understanding of the formula is useful as far as it helps you remember the formula. So I think it's actually easier to just remember the formula in this case. So don't get bogged down in the understanding of this one. Okay, so that's the last approximation I'm going to talk about. Now, let me talk about the select mortality, how we would deal with annuity contracts, life annuity contracts that have select mortality. So as before with assurances, it is no different in that all we are doing is notationally changing the life status to be just an X to an X in brackets, in square brackets. And then we must be careful if we do have to do something with first principles that we are using the correct probabilities that relate to the select period. Okay, so in other words, I'm saying that if it is still within the select period, we must use the select mortality for the life and the probability for that select mortality. But if the person is outside of the select mortality, it has already converged, we're assuming, to ultimate mortality, and so we start using the ultimate mortality probabilities. Okay, so I hope you found this video useful and interesting. If you have any questions, leave it in the comments down below. Thank you.